so maybe let me formulate some simple question, maybe natural for mathematician, and after that you explain probably what is going on. So, well, so what I can do, I can open a screen maybe, yes, and probably I can write. And so I can say very shortly what we heard. Then we have two things. We have vertex separator algebra business. And here we have something which is possible to call topology or algebraic geometry and so on. And maybe the typical situation which we heard is following. In vertex separator algebra side, we have Verlinde algebra. And very, very old story about Verlinde algebra saying us that if I have some SLN, for example, hat, or even G hat and some level K, then Verlinde algebra is conformal block for a torus. So we have to take elliptic curve for that. And considering the modular space of, for example, SLN bundles, and if it SLN bundles, that SLN bundles on E is just CPN. Just for SL2 is CP1 and so on. When K is hidden here, we need to consider just linear bundle, and the space of sections of this linear bundle is conformal block and for torus, and it is Verlinde algebra. So it means that space of sections of this has many additional structures, what Verlinde algebra has. So it has, it is algebra, it is a representation of modular group and so on. And also what is discussed in Dupé lectures that maybe it is, you know, in algebraic geometry side, surely this description, because we need some algebraic geometry, model space, and something like that. But here we have what? We have Grassmannian n-dimensional space in n plus m dimensional subspace, and then we can consider the cohomology of this. And also, according to very, very old, what Witten, maybe 30 years ago, something like that, that we can take this and we can consider the quantum deformation of this, make this quantum, and it gives us some algebra, and this algebra is isomorphic to Verlinde algebra for SL n plus m on level n. I think so, yes. And so first Verlinde algebra is here, and it looks like a completely different construction with this. And anyway, Dupé explained to us that no, the proof of this fact is no, in old it's just some checking, but it is possible, surely some conceptual way to see it. Why they give us the same things, and but what is going on here? That at least if we believe in this, it means that this kind of Grassmannian n plus m knows something about the vertex separator algebra which we have here. Knows in what sense? It is cohomology, and maybe K-theory is in charge of this, but at least when we want what Dupay said, for example, here, we have, no, if we are talking about equivariant case, anyways, here torus is acting here, and we have fixed points, and these fixed points are corresponding to cohomology or generators of K-theory and so on. And these fixed points, no, because this is Berlin the algebra, that so these fixed points are corresponding to objects in a corresponding tensor category or representation on this side. Therefore, we can take these fixed points, and after that, we expect to have, first of all, some tensor category where these points are associated with some objects. And also, and not only that, tensor category surely it is not enough. We have not only the tensor category, but much more than that, the conformal field theory. And in Dupay lectures, it's no, he mentioned this kind of story for sure, but he also said two things. One thing that which is probably one thing that here in this situation, or it is the deformation of Berlin the algebra, and maybe he even also explained some physics behind this. About corresponding T deformation here, he did not explain, but probably, or maybe he did, but I do not know. But it has to be some deformation here. Yes, but it is one thing which he mentioned. Other things that it is some kind, not industry, but better to say the theorems or guessing work or correspondence, I do not know, where in this side we have a big amount of some manifolds which appear of Coulomb branches of something, and in this side we have some collections of vertex separator algebra, and at least how it is going. So no, in some sense, it has to be similar to this. So I want to say, well, we have something, if it is some action of torus there, or something like that, we have fixed points, then we can construct or guess some kind of tensor category. But even more than that, we can find the corresponding vertex separator algebra. And the way of guessing such kind of guessing work, maybe if Serezha will say something about this, it will be nice. Because from the point of vertex separator algebra, here rather very subtle construction, rather complicated cassettes appear. And so how it is going on. And also even simplest case where here we have Virasoro theory like 2.5, or no, in some sense, this 2.5 seems to be the simplest, but it is not unitary. And so for example, in this situation, we have a unitary theory of SLN, And such kind of theory related with standard business is modular space. But if you are talking about 2-5, no, it is possible to construct 2-5 by several type of cassettes. It is also possible, well, but such kind of geometry, which is some counterpart of this, is not known, I think. But nevertheless, it appears by some way when we go from this to this. Yes, and so maybe for the people who understand more about this side, I mean about this side. So it means if you know about vertex separator, algebra, and connection with tensor category and things. So surely there are a lot of open questions here also, but conceptually it is more or less clear what is going on in this side. And also because it is conformal field theory here, the relationship within modular spaces of a band or something living in the modular space is also clear. And because it is tensor category, then it is also more or less clear the relationship with where tensor category or quantum group is used. It means that we can try to determine the invariant of three-dimensional manifold knots and so on. So from the it means that some kind of three-dimensional topological field theory is there. What really mysterious and ingredient of this puzzle is this. So we have some kind of yes, and I agree, but still I want to fix some question. Question is how it is going and how it is possible to think about this. Yes, and no, I can ask more question about this, but maybe I stop and maybe Serежа or Dupay or somebody else can explain something. Then let me go out and maybe Serежа, you can say something, could do also or so on. Just
since I have to decouple soon, so maybe if Do is okay, I'll start and he'll continue. Do is it okay with you?
Yeah, that's fine.
Are you able to stay a bit later today?
I think so.
Okay, so then you'll be taking over at some point when I have to go, unfortunately. But so let me try to give answer to these three questions the way I can. And again, you will say more. So I created the whiteboard and even copied the questions there. So unfortunately, I'm not at home right now, so I don't have technology to share the screen, but you can go on this whiteboard and I'll try to write there, and actually you also can write there if you want to make further comments. So from what Boris just said, I copied three questions. So I'll try to answer each one.
So somebody have to open the board, yes?
Oh yes, actually, if somebody who is on a real computer maybe can open the board and screen share, that's another option. Yeah.
Okay.
Oh, sorry, no, that's not the whiteboard. That's something else, right? Well, I mean so I created the whiteboard and shared it in the chat. If somebody can share that for Boris, because I'm not at home and not on a real computer. Oh, perfect, yeah. So can you see this, Boris?
I can. Yes.
In fact, if you click on the link in chat, you yourself can write and make comments and so on. But yeah, let me first start with question number 1. So the general, so do explain to you lots of things. And first I have to make a disclaimer that I don't want to be able to say better things that he already said. So he actually did a better job than I could. So listen to videos and look at notes. I think that's the best source. So what I'll say is probably complimentary and not sure if it will be helpful. So that's why I think his lectures are better and perfect compared to what I can say. But anyway, let me give it a shot. So for first question, I want to clarify maybe or emphasize one thing that among many different things that you explained to you, one general theme was basically relation between geometry on one side, and here I'll call geometry of this space X. So this is a manifold, so do call it MT in various lectures and via other letters. And on the other side, there is algebra, but algebra in the form of some kind of tensor category. So I'll call it MTC, even though, as Drew pointed out, it's some generalization of notion of MTC that you may encounter for various X's. But it's this dictionary that's supposed to hold in great generality and be fully, I mean, that was the prevalent theme in his lectures. So connection to VOA is additional ingredient, and it comes in several different forms. So maybe that's why it's best to separate relation to MTC, which is more solid and more systematic, whereas relation to VOAs requires some special circumstances. For example, yeah, so I won't try to say more about it. So then X is better be hyperkähler. And if you take any X, compact or non-compact, you're allowed to ask what is MTC on the other side. And basically that's a kind of question that Drew was trying to explain to us. And the answer may be complicated, the answer may be hard to figure out or interesting, but that question always makes sense. And physics answer, so I'll put it in quotes, sorry, in parentheses, because this is not important to math, but so you know, physics answer always exists. So it's basically a so-called category of line operators.
Sergey, I'm sorry, this Victor was trick. It's technical question. So for me, your screen is not moving. So, and I don't know whether it applies to everyone else, but.
Well, since, yeah,
I mean, I can see only kind of.
Right. So click. Right. So this.
Oh yeah, now it moves. Now it moves. Good. Now I can see.
But I'm not the one sharing the screen. So what I suggest, probably Boris is on tablet or iPad or something. Click on the link in chat. So I sent a link in chat.
Yeah, I did, but apparently I'm drawing some pictures on your notes, which I don't want to do. So.
Okay. There is this whiteboard works is on the left you have various tabs like draw, erase, and there is a very important button called move. So if you click on that, it will allow you to move the whiteboard with your mouse. So that's and you can actually move it completely independently of what happens here. So, okay, so then the answer to this question number 1 in terms of what generalizes the Witten's relation between Verlinde algebra and quantum cohomology of Grossmanian is a particular choice of X. So, and first, maybe I should make, so I'll now come back to this question, but I wanted to frame it in this bigger framework of relation between geometry and algebra. And I want to point out that relation to cohomology of Grassmanni and Berlin algebra, even in the usual case, so Boris was asking if there is something conceptual behind it. The only conceptual thing that I know involves physics of string theory, some D-branes and so on. In part, you can see that it's not something conceptual in math, because this relation is very nice only in Cartan type A. And in math, when something happens only in Cartan type A, that's a red flag, basically. It suggests that the representation theory is not as general or conceptual as you might hope it was. And that's really the case. That's the situation, at least as far as I know. But there is an explanation in the physics using string theory. I don't think it will be terribly useful, that sheds light on the original relation. But answer to a question about counterpart of the T deformation, that's also something that Du posted in chat, and that's easy to explain. So original Grassmannian of K planes in some n-dimensional space is what? It's something like, you can think about it in many different ways, but so for instance, it's homogeneous space. It's a quotient U divided by UK times UN, right? So that's one description, but that's not one I'm going to use. So there is another description, which is as a Keller quotient. So you take space V to nth tensor power, and V is going to be defining fundamental representation of UK. So V is defining fundamental representation of UK, so that this whole quotient is basically C to the dimension K times N divided by UK, but divided where U acts in a natural way, but also you impose the moment map, so that's why the double slash notation. So that's the Keller quotient. So the space, so this you need for Verlinde algebra. So this gives you Verlinde according to Witten. But then if you take X to be a very similar quotient, so you can take V tensor power N and also take a joint representation of UK and do this double slash. Then you get counterpart this T deformation of Verlinde. So that's the counterpart, and here you can actually see the T deformation also associated with the symmetry, namely there is U1 action, circle action here, which commutes with action of UK that gives rise to the T variable. So I may not get all the details right, but I think Du will help me later, and if I miss something, we'll clarify it here. So that's a very kind of concise answer to question number 1. So I'll try to go through all of them first quickly, and then again, maybe I can ask more questions, or Du can probably say a lot more about each one of them. So my answer to question number 2 will be even shorter. So if I understood the question correctly about this relation.
Serge, one short question about the first. That you said that we can take X in principle any Gifford-Keller manifold, yes?
Mm-hmm.
And we expect to have tensor category and also Verlinde algebra and things like that built from that, yes?
Yes.
This is true, so it means that no, it replaced Grassmannian, yes, more or less, or
Yeah, so it replaces Grassmannian. Grassmannian is not hyperkähler, but like I said, that in some sense, here it appears as, for example, part of the stationary fixed point set of this U1T symmetry is going to be exactly the Grassmannian itself. So here it appears as component. So in that sense, Grassmannian doesn't even fit in this general relations that Dew was describing between geometry and algebra. So it's better to have hyperkähler space. And Grassmannian is a bit special. It's only Kähler, not hyperkähler.
But still, it is something is working. But if we take, for example, Gilbert's scheme points on a plane, it is not compact but hyperkähler.
Yes. Oh, that's a fantastic example. Yeah, that's another. So if this was example number 1, then yeah, you can certainly take X to be Hilbert scheme. In fact, any non-compact space you want. Hilbert scheme, let's say, of n points on C2 mod ZM. You can even make it more interesting and consider other surfaces and so on. In fact, you can take K3. And then it's a meaningful question, what is the corresponding MTC on this side? Mm-hmm. And it's a good exercise. So probably Dew already knows answer, at least for some values of M, N, and so on, off the top of his head. But I know only for one value, M equals 1, N equals 1. But again, you can ask Dew later, and he can try to walk you through this. In fact, I think examples of this type we had in this last paper with Dew, Nakajima, and others. Mm-hmm, mm-hmm. So it's exactly for this kind of questions that this technology was developed, invented. And like I say, if X is really hyperkähler, compact, non-compact, singular, you always have a right to ask this question, and the answer always exists. In fact, it probably gives answer to Vita's question yesterday. It provides new types of interesting categorical structures which are beyond traditional MTCs.
Okay, maybe we will ask Dew about details in some simple examples like that. Simple or not, but at least this example is very nice. It has to be very...
Yeah, it's probably very nice. I like the Hilbert scheme. That's a great question. And while I'm finishing the other 2 questions on the list, maybe Dew will work out, or again, maybe he already knows the answer off the top of his head. Yeah, so going back to question number 2 that you asked, Boris, how we get collection of VOAs. So that's what I want to emphasize, at least in my understanding. Collection or VOAs appear in some special cases. So for instance, if X is a Hilbert scheme, I have no idea what VOA is. And again, I want to emphasize that this has to do with the fact that if you have geometry,
so connection is not very good. You disappeared for 1 or 2 minutes. Maybe it's only for me, maybe for all. I do not know.
Yeah, again, I apologize. I'm not at home, so I only have rather poor connection. I can try to turn off the video. I'm not sure if it's going to be any better. So let's see if this will work. But yeah, since I'm using whiteboard and then Zoom at the same time, it's maybe not ideal. Right. So here we have, again, this link between geometry and algebra. And then on algebra side, we have MTC. And of course, it's always, or sometimes it's natural to ask, is there a corresponding VOA, which in Vita's notation would be the same thing as 2-dimensional CFT. So for us, these 2 notions are more or less equivalent. So, and as Boris pointed out, of course, there are many VOAs which have the same MTC. So yesterday, this was part of the confusion, and that's of course exactly right. So in general, this link is not there, at least this kind of link. So I'll draw it as a dotted line, and I'll write that it holds sometimes. But this sometimes is not as universal as relation between X and S and T matrices that you see as part of MTC data. So modular data is more universal. So this sometimes gets realized in two different cases, and the realization is quite different. So first of all, if X is moduli space of G Higgs bundles on some Riemann surface sigma, then you get the story that involves both Higgs and Coulomb branches. So then there is, so previous story was about Coulomb branch, but then now there is also a Higgs branch in the game. And it is the Higgs branch that determines this VOA, but again, we have no idea what the analog is in the case of Hilbert scheme. That's the example you just asked. So in that case, we still can ask meaningful question about S and T matrices and compute them and so on and so forth. But we won't be able to tell, or at least I cannot immediately tell what the VOA is, because it's not exactly of the type of moduli space of Higgs bundles. So then the second sometimes option is goes via relation to quantum groups. So that's question number 3. So your question number 3. And here, for instance, if we have, yeah, so I'll say a few words about this in a second. So we'll have some UQ of G and its various cousins. So here there could be various connections to logarithmic VOAs, log VOAs, such as triplet and so on, triplet, singlet, and various generalizations that we all love. And again, in this small world, it's also systematic, but it's not as big world as a relation between geometry and algebra emphasized above. So in that sense, and there could be various other connections to VOAs. So I'll draw a third arrow, and I'll pose it as a question mark, because I think this is really a question for further research and that deserves to be understood better. So I don't know if it really clarified question number 2, but hope it did to some extent. Right. So question number 3. So here I can try to give a more conceptual answer from Bird's viewpoint, and then again I return the microphone to others to say more, ask more, and comment. But here I would try to draw the following picture. So we're discussing geometry of space X, which is hyperkähler, and then we're discussing some, on the algebra side, some kind of MTC that's really, again, it's MTC in codes because it may have not all the structures of a traditional MTC, but it's determined by hyperkähler geometry of X. And then in this greater generality, where we have this connection, it actually makes sense to ask about connection with TQFT, topological quantum field theory, or since I'm writing just branches of math, I'll say topology. So it involves invariance of 3 manifolds that you can compute using a TQFT, which, as Drew explained to you, is Rosansky-Witten theory. or he can probably say a lot more about it. This appeared only briefly. Rosansky-Witten theory of X. So where X is again a Coulomb branch, and this is what Ju called M in various examples and so on. And like I emphasized, the Coulomb branch is something universal, and the appearance of Higgs branch is less universal, should not appear. So connection between MTC and TQFT on the one hand is known and is closely related to, for example, what Vitya was describing to us. And geometry and topology, this link is achieved via precisely this Rosansky-Witten functor, except that you have to regularize various things, and T deformation and its close cousins are playing a crucial role. But then there is another element in this correspondence, namely, if you have sometimes, so that's also not quite universal, but sometimes you have relation to quantum groups. In particular, to the center of the quantum group. So that's, well, maybe I shouldn't be drawing.
Serge, can I ask about what you said? So X is manifold. It is some kind of Rosansky-Witten procedure which gives us invariants of three-dimensional manifolds, for example. Yes, and the example of this, if we have, in principle, what kind of invariants they are. If we have invariants of Reshetikhin-Turaev or things like that, and or Verzumina, but if suppose it is expanding K, and K expansion in infinity, first order, second order, and third order, and so on, give us maybe not precisely this, but something similar. Yes, so each term in K, in infinity, expansion, give us Rosansky-Witten type theory. Yes. So, or maybe each term, maybe each term is corresponding to some manifold, at least can correspond. But so it means that if I take X, by X, I construct something like some term in expansion of something from this point of view. Yes, but are you saying that these terms give us tensor category or something like that? Tensor category is a whole thing, but not a K-term expansion of something. So
that's right. So these are two different things, and I personally don't fully understand the relation or two different applications, let's say, of Rosansky-Witten theory. One is, as you point to, perturbative expansion. So maybe I'll write it below. So Rosansky-Witten theory, it's not quite a TQFT in general, but it is a TQFT when X is, for example, compact. And there aren't so many such compact X's, but if you increase the dimension, then you have more and more choices. And then you definitely get relation to this perturbative invariance.
Yes.
Perturbative, or also sometimes called Vasiliev invariance. So that's the whole story, and that's one fork in the road or direction we can go. Another is when X is non-compact. And here you get some kind of TQFT or MTC labeled by choice of X, and this equivariant circle action comes into the game. And this leads to something more exotic, more interesting. I don't know how it's related to the previous, to the first one, so I'll put it as a big question mark. I have no idea what the relations are, but when X is non-compact, the upshot from and when this U1 action that it carries, so again, Dew was explaining to you that it's very important to have a symmetry, so that you can use equivariant localization, at least one circle action. And when this circle action is triholomorphic, this is slightly better than U1 action on the moduli space of Higgs bundles, where it's only holomorphic. When it's triholomorphic, you expect that this TQFT is associated to non-semisimple MTC. And various other constructions that appeared in the literature and study of this invariance, such as ADO invariance. Oops.
Anyway, Fx is Gilbert's scheme. It is such kind of example, yes? And
yes, exactly. So in fact, if m is equal to 1 and n is equal to 1, it's a very famous TQFT. That's why I know the answer. And it is non-compact. It's exactly this kind of example. It does carry triholomorphic U1 symmetry, so it's expected to be defined on any 3 manifold. Again, our expectation is that that's more or less a general feature. We don't know direct relation. So there are several ways to regularize something which is non-semisimple. So one way is using this symmetries of X. That's more geometric way. Another way that people sometimes use more algebraic is based on theory of modified traces. So there are some infinities, and you have to say how you take a trace in a category or sum over things which are not traceable otherwise. So there must be a relation between this U1 equivariance and theory of modified traces. It has not been looked at, so therefore I cannot say anything about it. But morally, probably there is a connection between different ways of regularizing such things. In any case, you raise a very good point that there is an old story. So this perturbative business goes back to, I don't know, mid-90s, 1990, whatever, 5 or 7 when this came about. And here we're talking about 2020. So I have no idea what the relation between 2 different uses of Rosansky-Witten theory is. You're absolutely right. In one case, you get perturbative invariance, and you usually focus on numbers. You never, in that old story, ask about categorical aspects. And here, you get algebraic structures. Of course, you can also get numbers, but you get a whole category or TQFT attached to your space.
Seriously, but you're saying that this new things is not generalization of the old to non-compact situation. It is just another usage, or just it?
Honest answer, I don't know. To me, at this moment, it looks like it's independent, and Dew probably should comment because he may have more thoughts, or somebody else may comment. I personally don't know, so that's why I put 3 question marks here. It's a good question. To me, it's not obvious if there is a relation, but it looks completely different because because this modern thing gives you TQFT as a whole, whereas the previous story gives some perturbative expansion in H bar. And part of the reason it looks to me as they are independent, because often this triholomorphic symmetry that I wrote, I'll put a subscript Q, can give you Q series invariance of 3 manifolds. For example, if another cool example is we discussed cotangent bundles to Grassmannians, roughly speaking. These were not cotangent, but some other bundles when I added a joint. So take cotangent bundle to affine Grassmannian. So that's a good choice of X. It's infinite dimensional. It looks pretty crazy. but it actually is interesting, and you can even give you examples of calculations where what it produces as a result is a Q-series invariant of a 3-manifold. And morally, the Q that appears here in this story, so Q is exponential of h bar, whereas it's this h bar whose coefficients produce the invariance in the whole story. So in other words, here we get some number times h bar to the power n. So these are expanded around completely different points in a complex Q plane. So if I try to draw the Q plane, then we have a unit circle, and h bar expansion happens around here. So Q, which is exponential of h bar, goes to 1, whereas Q series sits here.
Mm-hmm.
So part of answering your question about how these stories are related would involve also transferring domain of expansion, because in this 2020 application, you get natural expansion around Q equals 0. That's when you get a Q series. Whereas in 1997 version, you get expansion in h bar, which is near Q equals 1. So again, I think, so this to me tells that the answer, if any, is not exactly obvious, but it's not to say that there shouldn't be. So maybe there is one.
Okay.
Okay. Anyway, yeah, I feel like maybe Du at this point should say, because I'm sure he can add a lot more, or Boris or somebody else.
Okay, thank you about this. And if you have some time, you can add some more, or
right. But yeah, first I should give the turn to others, and I don't want to also hijack the discussion. So maybe there are completely different questions.
Is this last relation between Q and h bar like in relation between Gromov-Witten and Gopakumar-Waffa?
Yes, it's exactly that. Yeah. So in fact, in that story, you also have Gromov-Witten invariance near here, near this region. So GW stands for Gromov-Witten, not for Gukov-Witten. And in this region, it's GV, also known as Donaldson-Thomas, Pandrea-Panda-Thomas, and there are many variants, but they're all pretty much the same. That's also the same as BPS. So these are Gopakumar-Waffa. And in fact, this Q-series invariance can be realized as Gopakumar-Waffa invariance. Perturbative Chern-Simons invariance can be realized as Gromov-Witten invariance. These are two separate lines of work, and this whole diagram commutes in that sense. So you can have also enumerative interpretation of this TQFT, three-dimensional TQFTs. Yeah.
And in story about Gromov-Witten, we have Chern-Simon theory as non-perturbative counting for this invariance. And in three-dimensional case, when we add one more dimension, what stands for Chern-Simon theory? For D theory compactified on S1 or what?
So you want to go to 4 dimensions or from 3D Chern-Simons to 2 dimensions?
No. I mean that in this old story about Gromov-Witten invariance, which was two-dimensional, we had Chern-Simon theory to compute like non-perturbatively invariance initially physically. But what stands for Chern-Simons in this when we start from 3-dimensional theory and want to count non-perturbatively?
Well, I'm not sure I understand, because Gromov-Witten is perturbative, even in the case of topological string or A model. So this is perturbative.
Yeah, I understand. I mean that like, if I understand right, the initial computation for Gopakumar-Waffe invariance was made using relation with Chern-Simon theory. Yes, and to infinity limit, like topological strings as Chern-Simon theory.
Well, that was only, yeah, so what they did is, that was only to check, but actually conceptually they did computation in terms of Q. So in this diagram, you should think that they did computation near Q equals 0, and then they tried to do the check that whatever they got, they actually tried to re-expand the answer in terms of H bar. So that's why they went one direction, from Q equals 0 to Q equals 1 expansion domain. And the reason was that in the case of free sphere, which was their example, or one can generalize it to length space, that's actually very easy to do. And they managed to do it. So for them, it was an obvious check. But in general, I would say that Gopakumar-Waffe, Donaldson-Thomas, PT invariants, or BPS invariants more generally, give you non-perturbative completion of Chern-Simons. That's the modern way people view it.
Thank you.
In fact, I think that's the viewpoint. For example, Marcus Mourinho is, well, I'm not sure what he does now, but 10 or 20 years ago, he was basically popularizing that this BPS invariants give you non-perturbative completion of Chern-Simons. And the reason is that indeed Q can be generic, basically, that this BPS story. So do you want to fill any gaps that
I think the only thing that I want to add about this connection between non-perturbative and perturbative aspect of Rosensky-Witten theory is that, first of all, for some non-compact manifolds, one can also apply this perturbative method, like for Atiyah-Hitchin manifolds, because the metric behaves nicely at infinity. Rosensky-Witten argued that, well, in the end, the perturbative invariant is some kind of integral over the over X, and as long as it's die off, the integrand die off at infinity, you can do the integral. So there's some kind of overlap between the two, and also for some compact manifolds like K3, one can also try to use a non-perturbative method. We can get some information such as action of mapping class group, SL2Z on the Hilbert space on 2 torus. If I remember correctly, in the case of K3, you have two-dimensional representations of SL2Z and like 16 one-dimensional representations. But I think it's not known how to make this into an MTC or some sort of graded tensor category. But it's expected to be a Z2 graded thing. But I don't know anyone has identified what exactly happened for the K3 Rosensky-Witten model.
So, sorry, can you tell more precise what you expect about this category? I mean, how many simple objects or anything? I mean, what kind of information you have?
Let me try to maybe again use whiteboard.
Yes, it's better.
You can use the same, actually. I think
yes.
It allows writing for everybody.
So for K3, one have a Rosensky-Witten model, and one can ask what is the Hilbert space on T2. This is identified with the Dobol cohomology for K3. So then you know that you have this familiar Hodge diamond. I hope I got, sorry, is it 16 or something else in the middle? Or 22?
The whole should be 24, right?
Yeah. 20? Is this right?
Yeah, this sounds better. It's too bad this is recorded. We're embarrassing ourselves.
Well, I'm not an expert on K3, so I think it's fine. And then, so the SL, well, so this space is doubly graded. And the SL2Z action does not preserve one combination. So it will rotate these two and these two, will leave this invariant. So it will be a two-dimensional representation, another two-dimensional representation, and bunch of one-dimensional representation, and the action of SL2Z. But this kind of action is weird. It's not like the usual unitary representation of SL2Z, right? So these two almost never arrive.
And this space is the structure of algebra also, yes? And
yeah, this has a structure of algebra. You can certainly multiply, but this is not, well, this is nilpotent, right? So it's also somewhat strange. I mean, the usual multiplication is nilpotent. So,
no, but it is usual multiplication, or it is.
So I think one should expect that it's actually modified. It should not be the usual multiplication. Otherwise, there's no hope of making this well-defined 3D TKFT.
But so it is usual cohomology, but probably the not precisely. We have to choose a little bit product you are saying, but it will be nilpotent algebra, yes, or.
Well, I think one need to modify the algebra such that it actually become not nilpotent. It should become well, maybe semi-simple in the graded sense.
Just semi-simple, so it means that some rational type algebra behind this, if it becomes semi-simple.
Well, I don't know whether being just like rational will be good enough, but I think indeed one need to modify it somewhat. So I think the first step is by not using cohomology, but upgrading this to K-theory.
Okay, fine.
And then maybe then do something else to get the correct version. The hint that it should be read from K-theory is that roughly you expect that the category that you associate to S1 is the derived category of coherent sheaf on X. And then this fellow has, well, if you decategorify, you naturally get some sort of K-theory. So from this point of view, it's more natural to use K-theory instead of this. So the action of SL2Z will break one of the Z grading. So there is only like a single Z grading that is preserved. And I think maybe one should actually expect that only the Z2 quotient is well defined. So this should be, if there is some kind of well, MTC in quote, it should be some graded MTC.
Do you know that the section of SL2Z factors through some congruent subgroup, something like that? I mean, so there is some big kernel of the section. This is something that happens for actions which you see at MTC.
So here, because the action I don't see this. So for example, T is just represented by this in this representation, right?
So T is not diagonalizable, yes?
Yeah. I think that's how, like, why this is a little bit strange.
This means that your category really should be something different from usual MTC.
Yeah, that's right. But then one thing that is slightly confusing is that you expect that this to be well defined on any three manifolds.
Connection is stopped again in my side.
Oh,
Yes, and again, one question that people expect to have the action of SL2Z or something like that on the category, on the derived category.
yeah, so on the derived category, there is some action of some autoequivalence of SL2Z. The S matrix is represented by roughly mirror symmetry. More precisely, if you consider K3 with elliptic vibration, you can perform some relative Fourier-Mackay relative to the base. And by homological mirror symmetry conjecture, you get the same category back. So this is the action of S. And for T, what one should expect is that T is, oops, I also lost the connection. So T is represented by tensoring with a line bundle. So
again, and such things is working if we have integrable system or such projection, fiber torus, and things like that. Yes.
Well, the interesting thing is that one should expect that this work in general, but we only know how to make this action concrete when there is a vibration. But for Rosani-Witten model, it's defined for any K3, whether it's elliptic or not.
Then it has to be some definition of SL2Z action. Yes.
There should be some SL2Z action. Yeah. For general K3.
And if we return to this archetypic case of Grassmannian, there we also have construction of SL.
Sorry, you mean for them the relation between Valenda algebra and like Grassmannian GR and M plus K? You mean here whether one can have a way of seeing the SL2Z action? Is that the question?
Yes, yes. By similar ways, there you had.
I'm not sure that in this case. Yeah, in principle, I think there should be a way. I don't know. I cannot recall exactly what happens. So there is a 3D theory with the target being Grassmannian, and that 3D theory, you can consider the Hilbert space on T2, and then that should have SL2Z action. I don't know how geometrically how to understand this. There is a question about what's associated to the two sphere. Yeah, I think that's a great question. So I think another very interesting question is what associated to the two disks. It's objects inside dx, and if you glue two disks, then you can get the two sphere. I think there's some work, maybe ongoing work by Braverman on something related to this. So some special, using some model that replace this dx, it seems that they have some understanding about what is this disk objects. But they're not exactly dealing with this category. It's some slightly simplified model for this category.
Mm-hmm.
Yeah, right. So but to answer this question directly, this Hilbert space is indeed expected to be I think just yeah, it's like the first. Well, if I remember correctly, it's like the first. It's that in K3, it's like two-dimensional space, and generated by some like constant function and the holomorphic volume form. Yeah, and just like what Sergey mentioned, the degree 0 piece of this space will be ring of functions on X. But there are like a higher degree pieces for K3. There is something also in degree 2.
Do, and maybe you repeat, maybe with some details, what you said about 2-5 series. So what we start with to get it, and
right.
Maybe you maybe you also mentioned some way to find characters of 2-5, but it is later. First, let us recall how to start and get tensor category and so on.
Yeah, so let me maybe just start with physical theory, this A1, A2 theory. So this theory is something that physicists would refer to as a non-Lagrangian theory, but there are still ways of studying it. One thing that one can obtain from the theory is it's a particular kind of partition function, sometimes referred to as a super conformal index. And it will be a Q series. And in this theory, people found that if you compute this superconformal index, the Q series that one can get is exactly the vacuum character of 2,5 theory.
But
this
can
is
you
one
give,
hint.
yes, can you give at least a hint how this calculation is going on? How we can get, from where we get this character of 2-5, for example? And
Well, that would involve a little bit more physics. So let me try. So this theory, although it's non-Lagrangian, there are ways of understanding this by doing something like RG flow. So start with some Lagrangian theory. Lagrangian means that it's a gauge theory, so you can write down the path integral.
yes.
And then there is a procedure to obtain this theory. And this Lagrangian theory will just have some gauge group, some G, and some matter, so or representation of G, and then something, some other piece of data known as through potential is defined by this data, and then there is some machinery to get non-trivial Q series out of this. So this is one way of getting this. Historically, I think this is not the first method that people tried. People use something else to get this vacuum character.
And
But
what
can
it be? If you to get character, it can be some kitchen recipe. Yes, it is possible to apply even without understanding. So how we how we do it?
Like how to do this computation, or
how to do this computation, or at least how to start. Surely we cannot have no time. Really,
right. So in some cases, it will be some integral over carton of G. So you have some dx, some kind of hard measure on T with some particular integrand that is specified by the representation and superpotential, roughly.
And what is X? T is maximal torus, or what?
Yeah, maximal torus of G. So there is a way of writing down some concrete formula for this theory, and to get this theory, I think one just remove some overall factors. It's some simple procedure, and in the end, you get some Q series, and you can compare that with this, and you find that indeed it just become vacuum character. 2.5 theory, 2.5 minimum model. Actually, one can do slightly better. One can look at certain operators. And these operators give some algebra. In this case, I think this is not exactly done this way. For simpler theory, there's a way to. So, a physical theory has many operators, and there is a subsector conjecturally that will lead to a VOA. But in this case, I'm not sure whether this analysis is exactly carried out. So I will refer to this operator as maybe Higgs operators. It's not terribly precise. Maybe Schur operator is a better name, but I don't want to explain why it's called Schur character. But it has something to do with the Higgs branch. There's a way to, in a sense, this VOA is a fancy quantization of the Higgs branch. I think this is roughly how people first arrive at this VOA. But then there's this connection via Coulomb branch. That from Coulomb branch, it seems that Coulomb branch know about modules for this VOA.
Now, Coulomb branch knows about tensor category, yes?
Yeah, exactly.
And this special case, what you are talking is, it knows about the tensor category of 2,5. So
yeah, that's right.
And you actually explained some kind of calculation where S matrices coincide with S matrix for 2,5. Yes.
Yeah, that's right. So, for example, fixed points. So remember that the space looks like this, and there are two fixed points on a singular fiber. This corresponds to the two objects, right, with this kind of fusion rule.
So again, this object is elliptic fibration, yes?
Yeah, so yes.
With one singular point.
One degenerate fiber.
Yes.
And for this fiber, there are two fixed points under the U1 action. And there is also a function on this space. Let's refer to this as mu. And mu evaluated at these 2 points is, well, exponential of this is roughly the diagonal entry of t. So at some point lambda, for either lambda equals to 1 or 5.
Yes, and as matrix is something which we probably explained, but maybe the question is this manifold, this Coulomb branch knows about Verlinde algebra with S matrix, and so or conformal block on a torus. Yes, but we can ask about the question if it conformal block on a torus or bigger genus, or we can ask about the not conformal block, but even we have CP1 with many points, and we can put representation, for example, non-trivial representation for this tensor category to each point, to these points. As a result, we get conformal block with the points, which Verlinde algebra is calculating the dimension of this, and it seems to be Fibonacci number for 2, 5, something like that. Yes, and we can see something which describing this in terms of Coulomb branch, just space which has dimension of Fibonacci number.
So maybe I should clarify that during the lectures, when I talk about Verlinde formula, it's in a slightly different context. There you have a family of MT that depends on sigma. Well, more precisely, T itself depends on sigma. And then you look at partition function of Rosati-Witten model with this target. And for the 3 manifolds being something like LK, 1. And this has a structure of 2D TQFT on sigma. So the story about MTC is about 3D TQFT on this M3. So in a sense, there are like 2 directions of some 5D TQFT. So for 5D TQFT, you can vary either sigma or M3. But for this quantity, it can be computed by doing an integral on this space. And because here we're talking about partition function on a length space, we expect that this is matrix elements like this. This is one way to get information of S and T matrices.
No, I'm asked only in this case or in general. So modular functor is no, well, modular functor in conformal field theory, if you have, for example, bigger genus, or you have a curve with the points, you can cook up some modular space and bundle there and take sections, and these sections will be just it. If we live in other side, in principle, probably we have similar things, even for Grassmannian, that Grassmannian and cohomology, or the form describing the modular functor for torus. And we can ask if we have not torus, but curve genus 2. And if we go along this line, we can expect some manifold such that homology, cohomology, I do not know what, or something like that, is this kind of conformal block for a torus. And similar story if we have some even CP1 and insertion of a points, and it is also have to be something topologically describing, and it is natural to expect, and this I do not know, and is it known something like that?
Right. So here, I guess the relevant question is to ask if I replace it, for example, with sigma times S1, then what I have? This is computing the dimension of a conformal block on sigma prime for this 3D T5T. In this present case, for example, indeed, you can get Fibonacci numbers and also something else. So for this, one can also write this partition function as index, as some sort of integral. Yeah, so again, there's some interpretation of this kind, well, with some integrand. So maybe I should write this with some particular integrand. But that will tautologically just give the so for this kind of conformal blocks, you can always, the dimension is just given by something that can be obtained from the S matrix, right? If there are insertions, you insert something else here. Sorry, S0, lambda, 1 minus G, something like this, with some insertion. So in short, the answer is yes. So one can generalize and get dimension of conformal blocks on general Riemann surface or Riemann surface with marked points with insertions. The insertion is, I think, is slightly well, it's easy to get the result with insertion by just taking this kind of perspective. On this side, it's not exactly clear what's the right thing to be inserted.
I see. Yes. So, well, I have surely I have a lot of questions to ask, but maybe somebody else can ask or say something.
Okay, let me use this opportunity. So can you say how this number 5, so you have fifth roots of unity in this example? Is it possible to see it from geometry somehow?
Yeah, so for example, this is a moduli space of some a solution to some PDE on this kind of geometry. And here there is some field that develop a singularity that takes the form of, I think, Z cubed, dz. Sorry. Well, there is some behavior of this kind. I forgot the exact power. I think it's actually the power should be fractional. And then you literally solve the Hitchin equations. And you see that around here, because of this higher singularity, you have Stokes phenomenon. And you have exactly 5 Stokes rays. And then what is this U1 symmetry? The U1 symmetry is generated by roughly combining a rotation of phi together with the rotation of the z coordinates or of this CP1. And
so
then
this Stokes phenomenon, you just basically count some powers and some differential equations, yes? So some
yeah,
power.
exactly.
Okay,
Yeah.
thank you.
There's another perspective on this. This kind of system is relevant for Penlevi-1 isomonodromy deformations of the Penlevi-1 equation. And there's a famous Z5 also in Penlevi-1.
By the way, speaking about famous, so Sergey, he's still here or not here. He said that theory which corresponds to m equals to 1, n equals to 1, something like this is really famous. I'm just curious what it is.
Sorry,
Yeah,
what m equals 1?
It was Hilbert's scheme. It was when we were talking about Hilbert's scheme of points on C2 mod ZM, and let's say n points on C2 mod ZM. So when m equals 1, n equals 1, it's just C2 itself, right?
Yes.
So that's a hyperkähler manifold, and it has a triholomorphic action. So this technology should give invariance of any 3 manifolds and so on. And the invariant is Torayev torsion.
I see. Okay.
It's also famous because it was rediscovered in many different forms. Seiberg-Witten invariants of 3 manifolds are equal to Torayev torsion and many other things. So.
I see. So you expect to have
Seriously,
some...
and yes, and tensor category in this case is what? 1 or how many objects? 1?
Well, it's again non-semi-simple, so it's symplectic fermions or the same thing as up to Z2 symmetry, like an Ising model. It's a 1,2 triplet MTC. So it has total of 5 objects, right? Because for p equals 2, triplet has 3p minus 1, which is 6 minus 1 equals 5. Right? If my algebra checks out.
So you're saying it is 1, 2, and number of objects. So dimension of Berlin, the algebra is 5, yes? 3p plus 1.
Yes, yeah.
And this 5 we can see from this simple geometry. What is this? Where is 5 here?
Well, 5 we can see from the usual pillowcase that you and I discussed sometime. So
no, we do, but
so it's but I mean there are several ways to see 5, but 5 is not the most interesting number in this case, in the sense that there is only one fixed point. So there are 2 crucial numbers for this special case. 5, that's 3p minus 1, but also there is a very important number which is 1, because there is one fixed point in C2 when you act with U1 action. And if you try to compute something, it's actually this one fixed point that's going to be playing most important role. So Duke can tell you all about, so he mentioned that S and T matrices labeled by lambda. So he, in his notation, which is still on the board, lambda is a fixed point, and he can write for you S lambda lambda, T lambda lambda in this case, so everything can be made super explicit. So.
But about logarithmic theory business, then if bigger Gilbert scheme, then 2 points, for example, then also logarithmic theory.
Well, it's probably, yeah, I don't know about CFT, like I say, we don't have direct ways to accessing conformal field theory in full generality. We only have ways to access some ST matrices and modular structure. So MTC, we can probably, it's a meaningful question. I don't know if Drew knows the answer off the top of his head, but at least in the paper, we give a method to compute SNT matrices for something like 2 points on C2. And then maybe Drew already knows the answer.
But in which case 5 is replaced by 3p minus 1, you know? Are there other cases where 3p minus 1 instead of 5?
You mean for general p, or?
Yes, yes, yes.
Well, those probably will be obtained by. So yeah, we were thinking about it and still discussing it. So it's best to embed this family if you want to get this triplets and 3p minus 1. It's best to embed them in a family related to this cotangent bundle to a fine Grassmannian. And then there will be slices in there. So, but that's slightly more delicate.
So maybe that was anyhow part of. So I have maybe more naive questions than the people before me. So you always said that, of course, I have this case when X belongs to a quantum group. So in which geometries then? Is that this tangent bundle or something?
Yeah, so it sounds like this cotangent bundle to a fine Grassmannian, or you can actually describe much better. If you remember, like I said, unfortunately, I'm not even at home, so it's not easy for me to pull even our paper and quote from there, but maybe he can do it in real time. So morally, it's cotangent bundle to a fine Grassmannian, and the reason it arises is because you can think of it as moduli space of Higgs bundles, kind of like what he was doing in this class, but when sigma is replaced by a disk, by a formal disk. And then it has two actions, actually. It has disk rotation, which will give rise to loop action on a fine Grassmannian and triholomorphic symmetry. And then there is also Hitchen's U1 action, which is what he called U1t, and gives rise to T variable. And but anyway, this model, this statement that it's cotangent bundle to a fine Grassmannian is not quite correct. One should use the right model for this space, and there are several natural candidates. One is just loop group of a complex group, but that's not the right one, although it's easy to say. But the right one is involves Braverman, Finkelberg, and Nakajima type construction that only you and Nakajima can explain.
I think it's just essentially a model of T-star Grassmannian that is easier to work with.
But I don't know if you can compute or give examples of this length space computation or Q-series. Anyway, maybe you can say more about it. I don't have details on my fingertips.
I'm not sure what to add. I think you have summarized this very concisely already. So I'm sure that many of you know this connection between quantum groups and this geometry involving a disk. There's an old story about maybe dating back to Witten and then Kumawafa, others. For now, Witten had this paper on transaminant theory as string theory, like this. And then if you take that geometry, you can rediscover geometry with a disk. So that lead you to consider model space of Higgs bundles on a disk. And then that naturally leads to this cotangent bundle of F and Grassmannian.
I see. So I was a little bit confused because I mean I know not enough about geometry, but so you had somehow it seems like you talk about two different TFTs, right? One that looks like something derived and one that's just the degree 0 part.
By the derived thing, you mean this Rosanti-Witten model?
Yes.
Yeah, it's right. So for Rosanti-Witten model, the gap between that and MTC, there are two things. One is exactly it has some graded. Well, all the Hilbert space is expected to be graded.
Yeah.
Sometimes like even doubly graded in the case of T2. Another problem is that the partition function is usually not well defined, especially for non-compact targets. And it's expected that when this target space has some nice triholomorphic action with some nice property, you can kill both of them at once.
So I tried to understand the zero part already. So Sergei said that it's functions on X itself. But what is the braiding? I mean, the modules over this are just sheaves, right? How is the braiding defined on OX modules? That confused me very much.
Yeah, so first, maybe easy thing is I should apologize for introducing confusion about this degree zero part versus derive. Du was correct to say that we have to consider Delbock homology, and when I was saying ring of functions, I meant ring of holomorphic functions, which is basically H0. So that was my context. And the reason I was thinking about H0 is that the invariant that this theory associates to S1 cross S2, in other words, if you try to trace over this Hilbert space associated to S2, that's going to be the Hilbert series. And that's what was top of my mind, because I was thinking about non-compact examples, and Hilbert series is naturally trace over this ring of holomorphic functions on X. So that's why I didn't think about higher part. But Du was absolutely correct to correct me that there should be also higher cohomologies and high degree pieces.
Yeah, but these two things are very interesting to me in their interplay. So that's why I was actually happy to get two different answers because they explain. So, but how? I mean, then. So for me, it was always if I have modules over OX for X some manifold, then there is no braiding in this category, right? I mean, at least not a non-degenerate braiding.
Well, I think this is exactly what Roberts and Willerton explained, that in Rosanti-Witten model, this category associated with S1 is a derived category on X, and that actually has a non-trivial braiding. It can be made into a braided ribbon category. And the braiding is only zero when, so this theory depends on a choice of homomorphic symplectic structure. If you tune that homomorphic symplectic form to zero, you don't have any braiding. But for that being finite, you actually have braiding.
So they use the Keller structure to introduce additional stuff on the braiding that would otherwise be trivial.
Yeah, I think it's that's fair to say.
That was very helpful. Thank you. And do you know this SL2Z representation on the zero part? So you said this complicated this interesting SL2Z representation. Now, if you just restrict to the zero part, do you know?
The problem is that somehow you cannot restrict to zero part.
In which sense?
Yeah, it will mix. So even in the case of K3, you see that somehow by acting on the degree zero part, you get something in degree non-zero.
So the cohomological degree we were just talking about is literally the 3 layers you wrote in your Hodge diamond?
Yeah, exactly.
Oh, that is very helpful. Thank you.
And also, maybe to add part of the motivation for why we were trying to do this and use these triholomorphic actions and find MTCs. So MTCs that we are finding associated to X are obtained using this regularization. So it's, again, think about analogs of modified traces that might be related to this. This gives some finite number of objects and some decent categories. So for example, for C2, we just discussed, you get something which is 1,2 triplet or symplectic fermions. These are not crazy categories. Whereas the reason I wrote to you this answer about ring of functions, already for C2, you see that it's horrible, it's infinite. And there is no natural SL2Z action, and I don't want to find SL2Z representation of infinite size. So that's already part of the disconnect, where taking naive answer definitely gives something that doesn't make sense. So question is, what would be the replacing infinite ring of holomorphic functions on C2? So in some sense, we want to keep the Hilbert series, we want to keep some information about it, but we want to regularize it so that in each graded piece, there is a finite dimensional TQFT or MTC.
I see. I was a little bit asking because we started with Schweigert in Hamburg and so on. We started to play around with sort of derived versions of modular functors for some non-semi-simple categories. But there, so you also get this graded structure, right? You can write down for triplet algebra what the result is, for example. So you get some derived thing where you see all this hierarchical homology of quantum group. But there the cohomological degrees do not mix. So that is a new feature, but maybe it's a good feature. Mm-hmm.
Yeah, it would be interesting to make this bridge. I don't think it has been explored, but yeah, as you say, maybe that's a good thing. So.
Yes, I see. Yeah, thanks very much for answering this.
Okay, maybe somebody else want to say. No, my point is that conference probably is too long. Maybe it's good to stop sometime. Yes, and yes, but anyway, this was so many things to discuss, and but right now, yes, and anyway. Maybe somebody can ask some question or say something.
Maybe I have a question about the first part of this discussion. What is a logarithmic VOA?
Well, Boris is in ideal position to answer this question.
No, I can say that logarithmic VOA, they appear. No, this is just what many people, Thomas and Vici, said, that it is a correspondence between quantum group and conformal field series. In principle, conformal field theory produces some tensor category, and quantum groups, and so if we go from conformal field theory to quantum group, what actually we do? We have to take the category of representation of vertex separator algebra, then look to the fusion structure there. But after it is not easy task, but after some work, we can find some tensor category, maybe symmetric one. Anyway, it depends from what we start. Yes, and if we have quantum group, in principle, we can try to construct corresponding vertex separator algebra, which well, and usually this correspondence is no, even if you have UQ SL2 and corresponding quantum group, then for example, we know that such quantum group is related with Virasoro. But Virasoro, for example, is not precisely that. The corresponding tensor category is bigger. Or if you, no, you can do something. But so better to say between quantum group and vertex separator algebra is some connection. In some cases, this is equivalence. But if you ask just questions, so from quantum group side, you have a baby quantum group. They are small, they are finite dimensional, so the corresponding tensor category is describable, not semi-simple, but still nice. Suppose you want to find vertex separator algebra which has precisely the same category, and if the correspondence is directly correspond this to that. In triplet algebra is this. It is what? No, in principle, the answer is what? If you have baby quantum group, you have not one, but actually many vertex separator algebra, conformal field theory, which just correspond to the same quantum group. And triplet algebra is one way to do it. Rather natural, but it is only one way to do it. And the algebra which Serежа mentioned is 1-2 type or symplectic fermion. It is one such kind of example where the corresponding quantum group is baby quantum group in the root of unity, and this root of unity is 2. Yes, and so well, so from this point of view, what is going on, we start with rather simple things, which is just C2. Then it is some way which we do not understand. No, I understand something, but I can't say it because I am not good person to try to explain, and I do not understand well at all. But at least the corresponding quantum group is the baby quantum group in the root of unity, which is equal to 2. And then the corresponding vertex separator algebra is what is corresponding to this. It is this triplet. Yes, and so this is the situation, and maybe what Dew mentioned, that in different cases it is some way to find 2-5 theory by some kind of calculation, and similar story about this triplet algebra. Also, some kind of calculation give you the character of this, and Serёж, you are here, Serёж.
Yes, I'm still here, but I'll probably need to go
so soon you go, but I know, I think soon we stop. But I only want to say that the character of triplet algebra is related with this z-hat business, and so they're given by some integrals, and these integrals give you a character. And I understood you that if you get to 5, it is similar story, different but similar. You also have something, and if you write down some integral, and you can find 2-5 character by this way. Is it true or not?
Yes, but I don't know a direct relation between 4D superconformal index related to Higgs branch that Dew was describing, and Z-hat, which is computed using Coulomb branches, and what we were also related to this affine Grassmannian. So that's part of the reason why, to me personally, this connection is mysterious, and I usually don't want to bring it up unless absolutely necessary. So it's if it's true, it's probably very deep connection involving 4D mirror symmetry or symplectic duality, which is not known. But it is true that you can compute Z-hat, for example, using affine Grassmannian, and again, Dew is a great person to explain at least some examples like length spaces, maybe, and so on. And that's the framework in which, at least to me personally, many of these things like log VOA, quantum group, and Simon's question about 1 comma p for general p tie up together. So it's inside this affine Grassmannian model and various slices there. So that's the best I can probably say.
Oh, may I ask?
Yes, yes, sure.
So if I want to ask, you have X and you attach to X SNT matrices, but so if it depends on how X is presented, maybe as a quotient or something like that. So does this construction depend on well, maybe it depends, but maybe eventually it doesn't depend, or it does.
I think it's expected that it should not depend. But of course, there can be some subtleties, like if you want to regularize. So if X is non-compact, you want to regularize. Maybe the regularization procedure somehow will depend on the presentation that you use. But I think the philosophy is that it should not depend. Whatever way that you choose to regularize to get some MTC, the SNT matrices should just depend on geometry of X, not how it's like constructed.
Okay, thank you.
Yeah, I think this is also related to this discussion about SNT action on a derived category. Like for elliptic K3, it's easier to see this, but somehow it's expected that this work for general K3, not necessarily elliptic. And it's somewhat mysterious for me how this works in general. But we certainly expect that there is some SL to Z action there.
Okay, so well, I think that now learn, you are here.
Yeah.
Yes, I think it is time to stop. And no, people are tired, and
Okay,
And we should thank Leonia and Boris for organizing this. So thank you.
no,
Thank
it
very
is.
much.
And thank you very much for coming.
Thanks for the
No,
Especially
no, conference is better
speakers.
than I thought. It's okay. It's okay. Yes, and so thank you very much. And no, it is really good. And maybe after some time we try to organize again something like that. Why not? It is good, especially if these things with coronavirus extend. In this case, it is easy to organize this. Otherwise, it's much more complicated.
Yes. There have to be some advantages.
Yes, yes.
Otherwise, it would be bad.
Anyways, thank you very much to all, and